Welcome friends to this new lecture of soil science and technology, and we are going to start a new week of lectures, and we'll be starting week 5, and from this week we'll be starting soil chemistry and other chemical processes related to soil. And last week we have covered different soil physical process. So from this week onwards we'll be covering different soil chemical process. So in this lecture we'll be talking about a most important soil fraction, that is clays and their internal structure. So basically they are made of silicate, that's why we'll be calling them silicate clays. So let us start today's lecture, and in this lecture it will take probably consecutive 2 lectures to complete the silicate clays, but we'll try to cover this following concept. We'll try to cover the soil colloids and their types, and then what are the silicate clays, and then we'll cover what are the basic structures of silicate clays. Then we'll discuss about types of crystalline silicate clays, and then X-ray diffraction analysis. So let us start with the colloid. So I hope that you know that a colloid is a two-phase system where not only where only one finely divided phase is dispersed in another phase, and the phase which is finely divided phase is called dispersed phase, and this the other medium is called dispersion medium. So a colloid is basically a two-phase system where dispersed phase is dispersed in dispersion medium. So example, let us see some example. Some common examples are clay in water, which is basically solid, which is dispersed in liquid dispersion medium, and also cloud in atmosphere, where basically liquid is dispersed in the gas. And remember that in case of soil, so if we narrow down to the soil, we'll see that all the particles which are having size less than 2 micron or 2 micrometer are called the soil colloids. Now these particles which are less than 2 micron in size basically combine both clays and humus fraction. We'll see in a couple of slides what are their distributions. And then obviously there are majorly 2 types. One is soil inorganic colloids and soil organic colloids, and in soil inorganic colloids basically clay and different iron and aluminum oxides basically are there, whereas in case of soil organic colloid, it basically composed of humus fraction. So these soil colloids are very much chemically active, and they greatly impact ecosystem functions. So we'll in coming days we'll learn that how they impact different soil chemical as well as soil physical processes. So let us go to the properties of soil colloid. Well, there are certain properties of soil colloid. Obviously, they are very extremely small in size, and also they have very high surface area. They have very surface area, and they have charges which are predominantly negative charge, and obviously there will be adsorption of cations and anions, and in these soil colloids, the surface of the soil colloids. Now adsorption is a surface phenomena against as compared to absorption. So adsorption is a surface phenomena where all the cations and anions are attached to the surface of these organic colloids. So colloid form an ionic double layer. We'll learn what are the ionic double layer, and basically, the ionic double layer consists of an inner anionic or cationic layer with adsorbed outer cationic or anionic layer. We'll discuss that later on. And obviously, another major property of these soil colloids are, they can absorb water, and due to absorption of water they can produce different shrinking and swelling of clay. And you have learned from soil classification that these vertisols, which are having high amount of clay, they can exhibit these shrinking and swelling properties, and we'll discuss what are the reason behind these shrinking and swelling properties of the clay. So let us go to the next slide and see what is unit cell. This is a very important concept. Now, if you consider, let me show you. So, this is a crystal lattice. This whole is a crystal lattice. Now, you know about the lattice and crystal, and each crystal lattice is made of some simplest repeating unit. We call it the unit cell. Now, this is a unit cell. Now, this unit cell will repeat itself to create this whole crystal lattice, and it repeats itself in 3 dimension to form the total crystal lattice, both in x, in x direction, y direction, as well as in z direction. And remember that the basal spacing plays a fundamental role in the identification of clay mineral specimen by X-ray diffraction. What is the basal spacing? The basal spacing is the spacing between two successive similar lanes of atoms, and we will discuss that later on. So, this basal spacing is very much characteristic feature for individual clay mineral, and based on this basal spacing we can differentiate one clay mineral to other clay mineral. We will discuss that later on. So, you have basic idea what is unit cell and what is crystal lattice. So, similar construction of similar construction can be found in clay also. We will see that in a while. So, let us go to the next slide and see what are the different types of soil colloids. Well, soil colloids can be differentiated into 4 different 4 major groups. One is crystalline silicate clays, another is non-crystalline silicate clays, then iron and aluminum oxides, and finally organic colloids or humus. So, this crystalline silicate clay is basically composed of some clay minerals like kaolinite and smectite. We will discuss their structure and properties later on. Non-crystalline clay minerals means they do not have any crystalline structure. So, some examples are allophane and imogolite. Allophane mainly occurs in the volcanic soils. Iron and aluminum oxides are, some examples are gibbsite and goethite, and these three basically collectively called as a soil inorganic colloids, whereas soil organic colloid composed of humus, and we will discuss humus in the later while we be discussing soil organic matter in later part of this course. So, we have learned about the different types of soil colloids. So, let us go and see what we mean by crystalline silicate clays. Now, crystalline silicate clays also has a layered structure with 2 to 4 sheet per layer, and if you see, this is a crystalline layer clay mineral. This is kaolinite, one of the most prevalent clay mineral. So, this is the kaolinite structure under the electron microscope, and you will see these they are made of these sheets like in structure. So, hexagonal sheet like structure. So, these hexagonal sheet like structures stacked upon each other to form this total silicate crystal. And remember that these crystalline silicate has layered structure, as you can see here. These are individual layers. So, with 2 to 4 sheets per layer. So, we will see in details about, we'll see in details about the structure. So let us also they are predominantly negatively charged. Remember that these crystalline silicate clays develop a huge amount of negative charge, and how they develop this negative charge we'll discuss later on due to different types of chemical process. And also they have diverse soil properties, or they have diverse properties. We'll also discuss that later on. Now, another important class of soil colloid is non-crystalline silicate clays. The non-crystalline silicate clays, because they do not have any ordered and crystalline structure, and they have high amounts of positive and negative charge. They develop both positive and negative charge, and they have high water holding capacities and low stickiness. What you have already learned about the stickiness and different classes of stickiness in soil consistency lecture. So these non-crystalline silicate clays are having low stickiness, and one predominant example of this non-crystalline silicate clays is allophane, and this allophane basically occurs in volcanic soils. So the third major class of soil colloid is iron aluminum oxides, and they are basically found in highly weathered soils, and they may be crystalline or sometimes amorphous, and they have low plasticity and stickiness. So you can see some iron aluminum oxide. Obviously gibbsite is goethite is one of the major iron oxides which is present into the soil, as well as gibbsite, which is one of the major aluminum oxide which is present in the soil. So these are also considered as soil colloid because they show different types of properties, which different types of properties generally shown by colloids. So the final one, the organic one, is humus. So this is the smallest of all soil colloids, and these are basically made of partially decomposed cell walls and biomolecules. We will discuss their structure later in this course, and they have very high water absorbing capacity, and also net charge of humus. Remember that it is always negative. So we have covered the basic overview of different soil colloid classes. So let us go ahead and see what are silicate clays. Now all the minerals, if you see, which are present in nature, you can classify them into 6 major categories, starting from nesosilicate, then sorosilicates, then inosilicates, then cyclosilicates, then phyllosilicates, and then tectosilicates. So what is what is the building block of this type of structure? Well, in any silicate mineral, the basic building block is called silica tetrahedra. Now let me show you so if we let me increase the size of the marker a bit so that it can be visible. All right. So this is the example of a silica tetrahedra. Now the silica tetrahedra is basically composed of one silicon atom at the center, followed by 4 oxygen atoms at 4 corners, making a tetrahedral structure. So basically it is SiO4 or silica tetrahedral structure. Now when a silica tetrahedral structure appears in the nature as a separate, they are separate entity. So in that case we will call them nesosilicate. So nesosilicate are basically composed of only one silica tetrahedra. The second category is called sorosilicates. Now sorosilicates are basically 2 or more linked tetrahedra, and these tetrahedra are basically joined by sharing their apical oxygen, as you can see here. So this is an example of the sorosilicate, and obviously the basic structural unit of sorosilicate is either Si2O7 or Si5O16. the third is inosilicates or inosilicates. Now, inosilicates is basically single or double chains of tetrahedra. And the basic building, basic structural unit is either SiO3 or Si4O11. Now, you can see this is an example of inosilicates where it is basically composed of single, or it is basically single chain of tetrahedra which form by sharing their apical oxygen. And the fourth one is cyclosilicates, and this is an example of cyclosilicates. Cyclosilicates are basically single or closed rings or double rings of tetrahedra. As you can see, this is a closed ring of tetrahedra, and this is an example of cyclosilicates. And the fifth one is the most important, and this is called phyllosilicates. Now, phyllosilicates are basically they looks like sheets of tetrahedra, and you can see these are all these tetrahedra are sharing their oxygen to form a sheet like structure or tetrahedral sheet, and this type of sheet like structure you can see in the phyllosilicates. And this phyllosilicate name comes from phylla or leaf like structure, and the basic unit of this phyllosilicate is Si2O5. And why we are highlighting these phyllosilicates? Because all the clay minerals which we will be discussing, all the clay minerals belongs to this phyllosilicate structure. And the final one is tectosilicates. Tectosilicates is most stable because it is composed of a framework of tetrahedral structures, and the basic unit is SiO2. Some examples are primary minerals like quartz is a very important example, and these are widely spread in the nature. So, these are the basic classification of silicates, and this is we call silicate clays, and because and the name is phyllosilicates, and these are other silicate minerals, and these minerals are mainly present in primary minerals, and also this tectosilicate is also present in primary minerals. So, we have covered what are the different types of silicates. So, let us go ahead and see how a crystal lattice of soil, of crystal clay lattice looks like. Now, a crystal clay lattice basically looks like this picture, and as you can see, basically a clay particle or clay crystal is basically made of these unit cell. These are unit cell. So, these unit cell basically produce ionic double layers, and in between the ionic double layers by how? Because these individual unit cell is develop high amount of negative charge at their surface. We will discuss how later on, and as a result of the development of negative charge at their surface, all the different types of cations are absorbed at their surface, and as a result they form ionic double layer. So, basically negatively charged colloid, when it is surrounded by different adsorbed cations, then it forms the ionic double layer. Not only that, and there are two types of surfaces, external surfaces and internal surfaces. Obviously, in between two layers you will see the internal surfaces. So, it is an internal surface, and external surface is this and this. These are some examples of external surfaces. Obviously, these are present in direct contact with soil solution, and these soil solution basically composed of they basically contains different types of cations as well as different types of anions like chlorine and different like chloride, nitrate and so on and so forth. So, this is basically a structure of silicate clay crystal which is made of which is made of this layered structure, and in between the layer there is called the interlayer space and external surface also available, and all these spaces are accessible for different cations and anions which are present in the soil solution for adsorption. So, let us focus on the silica tetrahedra and their related structures. So, as you can see, as I have discussed that this is the silica tetrahedra which is composed of 4 equidistantly placed oxygen atom, and in the inside there is a silica atom. So, and the building block is obviously SiO4 minus, and the angle is 109 degree, and this is an individual silica tetrahedron. So, when all the silica tetrahedra share their one oxygen with the adjacent tetrahedra, they form a sheet like structure just like this. So, this is called a tetrahedral sheet, and this is one of the major important sheet which is which compose the which actually builds the soil soil clay structure. So, so this is silica tetrahedra. So, if you go to the next slide, let us see what is another building block. So, another building block in soil is the aluminum octahedra, and this aluminum octahedron, the individual aluminum octahedron is basically made of the central aluminum, and which is surrounded by 6 hydroxyl hydroxyl anions or hydroxyl groups, making a octahedral structure. So, the central cation is either aluminum, sometime it is magnesium, we will discuss. So, in which condition magnesium occupies the central position, and remember that all the other surrounding hydroxyl group, they create a a octahedral structure. So, that is why we call it either aluminum octahedral or magnesium octahedral. So, all these aluminum, when couple of aluminum octahedron share their faces and sides with the adjacent octahedra, they form also a sheet like structure, we call it octahedral sheet like structure. So, we have the tetrahedral sheet and we have octahedral sheet. So, based on the arrangement of this tetrahedral sheet and octahedral sheet in unit cell, there are different types of classes of silicate clays, and we will discuss that later on. So, let us go ahead and see how this tetrahedral and octahedral linkage. So, if we consider a unit cell, if we consider this an unit cell, this unit cell is basically, we call it 2:1 trioctahedral mineral. Now, why we are calling it 2:1? Because you can see in the middle there is an octahedral sheet which is sandwiched between 2 tetrahedral sheet. So, that is why we call it 2:1. So, 2 stands for 2 tetrahedral sheet and 1 stands for 1 octahedral sheet. So, how they link together? You can see these red solid structures are basically denoting oxygen, whereas these are silicon, and these are basically magnesium. So, magnesium, this is basically magnesium octahedra, and in the magnesium octahedra these yellow balls are basically hydroxyl, and these reds are basically oxygen. So, basically these tetrahedral sheet and octahedral sheet join together by sharing their apical oxygen together. By sharing their apical oxygen, these octahedral sheet and tetrahedral sheet join, and as a result they form this 2:1 structure. Sometime you will see the structure is 1:1 structure, that means there will be only one octahedral sheet and only one tetrahedral sheet. So, based on the number of tetrahedral sheet and octahedral sheet in a unit cell, we can differentiate a clay into 1:1 type of clay and 2:1 type of clay. Now, what is the shorthand notation of this clay structure? Obviously, you will see, since it is a 2:1 structure, this is tetrahedra, this is TET stands for again another tetrahedra, and in between there is an octahedra sandwiched. So, now probably you have understood what is 2:1 and mineral. Now, another question comes, why we are calling it trioctahedral and what is dioctahedral? Now, you see, as a result of these tetrahedral and octahedra arrangement, there are obviously in this case we are calling it dioctahedral, and in this case we are calling it, in this case it is trioctahedra, and this is called dioctahedra. Okay. Now, trioctahedra and dioctahedra. Why we are calling it dioctahedra? Because you see, there are 3 octahedral positions. Octahedral positions are, this one is the first octahedral position, this one is the second octahedral position, this one is the third octahedral position. So, when all the octahedral position, all the 3 octahedral positions are filled with cations, then we will call it trioctahedral. And when 2/3 of these octahedral positions are filled, as you can see here, then we will call it dioctahedral structure. Now, in case of trioctahedral, obviously to satisfy, there will be magnesium, because Mg2 plus multiplied by 3. So, there will be 6 plus, whereas the similar charge can be produced in dioctahedral when there will be aluminum 3 plus multiplied by 2. So, 6 plus. So, obviously, the net charge is same, however, the numbers of cations are different. Here the aluminum is prevalent in case of dioctahedral structure, whereas in case of trioctahedral structure you will see magnesium is prevalent. So, I hope that you can understand now what is the difference between trioctahedral structure and dioctahedral structure. Okay. So, based on these 1:1 layer or 2:1 layer, and whether it is trioctahedral or whether it is dioctahedral, you can differentiate the soil clays into the following categories. So, obviously, the broad categories are trioctahedral and dioctahedral, and among the broad categories of trioctahedral, if a soil is only consist of a octahedral sheet, there is no tetrahedral sheet, and in case of trioctahedra, it will be only composed of magnesium, and in case of dioctahedral structure, it will be composed of aluminum 3 plus, as I have already told you. So, example is gibbsite LOH3 and brucite is magnesium hydroxide. And trioctahedral 1:1 type of mineral is example serpentine. You can see only one tetrahedra and only one octahedra. Here there is only one tetrahedra and another one octahedra. However, the difference is, in this case this is dioctahedral. Example is kaolinite. Kaolinite is one of the major clay mineral, and if we consider 2:1 type of mineral, obviously the 2:1 type of trioctahedral mineral example is pyrophyllite, whereas 2:1 type of dioctahedral mineral is talc. So, these are some broad classification with some examples. Okay. So, let us go and this is our final slide for this lecture. If you see, this is a relationship between planes, sheets and layers. So, if we consider, this is basically a silica tetrahedral sheet, and you can see some basal 3 oxygen and one apical oxygen, and in this is silicon atom. And obviously, in case of aluminum, in case of octahedra, the central atom is either aluminum or magnesium, followed by surrounded by 6 hydroxyl anions. Now, this is a unit cell structure or layered structure. In the layer, you can see it is a 2:1 type of mineral. So, obviously, one tetrahedral sheet, one tetrahedral sheet, one octahedral sheet. Octahedral sheet is sandwiched between tetrahedral sheet, followed by another repeating unit. You know that inside a clay structure, these unit cell will repeat itself to form a total clay crystal. So, so there is another repeating layer, and so this is a layer and this is a layer, and in between these two layers is called interlayer space, and this interlayer space is where different types of cations and water absorb, and the total summation of these interlayer space as well as these layer structures are called the crystal. So, soil crystal is made of both these layers as well as these interlayer space. Okay. And obviously, you will see different planes of a 2:1 type of mineral. 2:1 type of mineral, you can see you know, at the basal, at the base, you will see both silica and oxygen plane, where, you know, from silica tetrahedra, followed by oxygen and hydroxyl plane, and therefore aluminum and magnesium plane, and then oxygen or hydroxyl plane, and then again the repeating unit. So, this is, you know, a overview of a soil structure or soil clay structure, and we will stop here, and these are very much interesting thing, and we will learn new things in the next lecture. So, let us wrap up here, and then we will discuss these more in our coming lecture. Thank you very much.